Welcome to the deep dive. Today, we're jumping into a field that's, well, it's quietly shaping our world. It works beneath the surface, even inside us. Biomedical signal processing. We've been digging into an introductory lecture. It's from Dr. Kunal Pal for a course, BM6301.
Right, a foundational course.
And our mission today, it's really to grasp how signals, especially from our own bodies, are captured, decoded.
Yeah, how we make sense of them.
Exactly, how maths transforms them and what the cutting-edge techniques are. So by the end, you, listening, should have a much clearer picture of this, well, this invisible language of life.
It's happening all around us.
Okay, let's get into it. Even if you're not a biomedical engineer, you're constantly dealing with signals. This should hopefully give you that aha moment about what's going on under the hood.
Especially with health, yeah. It's really amazing how universal this idea of a signal is. You can almost think of the body like an orchestra, you know?
An orchestra, how so?
Well, constantly producing sound, light, electrical impulses, signals, and biomedical signal processing. That's how we don't just hear the music, but interpret it.
Ah, okay. Getting the meaning.
Precisely.
Right.
Transforming those raw physiological signals into insights. Insights that can, literally save lives. It's this powerful mix of biology and engineering.
Okay, so let's start right at the beginning then. What is a signal?
Fundamentally, the lecture defined it as a function that conveys information.
Right. Information about some phenomenon, its behavior, its attributes.
So basically, any way information travels, we often think time-based, like a heartbeat. Right?
Yeah, that's common. But it could be space, like in an image.
Or other variables too, and they are, wow, they're everywhere. You're sort of swimming in them constantly.
You really are.
Think about it. Audio signals, like us talking now, or music. Visual signals, TV, videos, photos on your phone.
Sure.
Even a simple thermometer. That's using a temperature signal.
And it goes way beyond that, doesn't it? Electrical signals in your appliances, your phone.
Right. Biological signals, heart, brain, muscles communicating. That's core to what we're discussing.
Yeah.
Then communication signals,
Right.
Wi-Fi, Bluetooth, texts, they're all signals.
Light signals too. Traffic lights, fiber optics.
Exactly. And even touch signals, like the vibration on your phone. Haptic feedback.
Huh. Never thought of that as a signal.
But it is. It's conveying information through touch. What's amazing is realizing that, well, pretty much everything around us and inside us is a signal. It's carrying information.
It's like the universe is constantly talking.
And we're just learning the languages, yeah.
So if everything's sending out signals, these information carriers, what do we do with them? How do we make sense of it all?
Okay, now we're getting to signal processing.
Right.
It's basically the toolbox, the techniques, the operations you perform on signals
To do what exactly?
to pull out useful information. Or maybe enhance certain features, make them clearer, or just transform the signal into a different form, maybe one that's easier to work with.
And this works for both types, analog and digital.
Absolutely. Old school radio waves, or the ones and zeros of digital data. The principles apply.
So what kind of tools are in this toolbox? The lecture mentioned a few key concepts.
It did. Key operations like filtering. That's crucial. Think of it like cleaning up static on a recording.
Okay, removing noise.
Exactly. Then transformation. Changing the signal's perspective, maybe from how it changes over time to looking at its frequency components, like seeing the individual notes in a piece of music.
Ah, okay, like Fourier transforms.
That's a major one, yes. Then modulation, like AM/FM radio uses to send signals over the air.
Wrapping the message.
Sort of, yeah. Convolution, which is, well, a bit more technical, but fundamental to how systems respond to signals. And compression.
Oh, like zipping files, making things smaller.
Pretty much. Reducing data size without losing the important stuff. Hugely important when dealing with massive signal data sets.
And this is where it gets really interesting for, everyday life, you might not realize, but signal processing is everywhere.
It really is.
Telecommunications, right? Making calls, using the internet, that's all signal processing.
Underpins the whole thing.
Medical imaging, MRI, CT scans, helping doctors see inside us.
Enhancing those images, making them clearer.
Audio engineering, getting that crisp sound in music and movies.
Definitely.
But also things like control systems in factories, speech recognition on your phone or a smart speaker.
Even financial markets. Analyzing trends.
Wow, it really does turn raw data into something useful, into action.
It bridges that gap.
Okay, let's zoom in now, bring it even closer, inside us. Biomedical signals.
The body's language.
The lecture defines them as electrical, chemical, or physical signals generated by our own physiological processes.
the body's internal communication network.
And they're absolutely vital in healthcare, aren't they? For
Right.
diagnosis, monitoring, treatment.
Couldn't do modern medicine without them.
The lecture listed some key examples. You've probably heard of the ECG, right? Electrocardiogram.
Or EKG, yeah. That's the heart's electrical activity. Its beat, its rhythm, very familiar. Then the brain, the EEG, electroencephalogram.
Mapping brain waves. Thoughts, sleep patterns, neurological conditions.
And muscles.
Yeah.
That's the EMG, electromyogram.
Correct. Monitoring muscle activity. But there are others too.
Like?
EOG for eye movement, PPG. You see that in pulse oximeters, measuring blood volume changes.
Oh, the little red light thing.
Often, yeah.
Yeah.
Then blood pressure, BP, spirogram for lungs, GSR galvanic skin response linked to stress or arousal.
Skin response.
Sweat
Oh.
gland activity, yeah. Plus basic temperature and oximetry itself measuring oxygen levels.
It's incredible, all these signals constantly happening inside.
And they give us such deep insights into health. For diagnostics, they're like little flags helping spot diseases, sometimes really early on.
Before you even feel symptoms.
Potentially, yes.
Yes.
Or confirming a diagnosis. For monitoring, it's about tracking things over time. Is
Um,
disease getting worse? Is the treatment working, keeping patients safe during surgery, for example?
Right. Then you have therapeutic devices. Pacemakers are a classic example. They listen to the heart signals and intervene based on them.
Using the signal to fix the problem.
Exactly. Neurostimulators, too.
Yeah.
And think about all the wearable tech now. Fitness trackers, smartwatches,
Constantly monitoring heart rate, sleep.
all based on processing these biomedical signals, giving you personal health data. And, of course, in research, analyzing these signals is fundamental. Understanding physiology, developing new tech.
It really is like listening to the body's private conversations.
That's a great way to put it.
So if that's the body's language, then biomedical signal processing. That's how we learn to speak it, how we translate it.
Precisely. Applying all those general signal processing tools, filtering, transformation, etc., specifically to these body signals.
The goal being
Extracting meaningful information, enhancing the quality, cleaning them up, ultimately enabling accurate diagnosis, good monitoring, effective treatment, turning that complex body data into clarity.
and getting that clarity involves specific steps, right?
Yes.
Objectives.
Yes, very specific goals. First, noise reduction. We mentioned signals are noisy,
Electrical interference, movement.
all sorts of things. So you need to filter that junk out to see the real signal underneath, like cleaning static off a radio.
Makes sense. What else?
Feature extraction. This is about finding the important bits, the specific patterns within the signal.
Like.
The QRS complex in an ECG that spikes showing the main heartbeat, or specific brainwave patterns in an EEG that might indicate epilepsy. Finding this signature.
Got it. The aha moments in the data stream.
Exactly. Then compression. These signals can generate huge amounts of data, especially over long monitoring periods.
Right. Storage could be an issue.
And transmission. So you need smart ways to compress it without losing vital medical details. Segmentation is another one.
Segmentation.
Breaking the continuous signal down into meaningful chunks, isolating individual heartbeats or breaths or specific sleep stages in an EEG.
Chopping it up logically.
Yes. Then pattern recognition, using algorithms to automatically spot known patterns. This is key for automated diagnosis or alerts.
Letting the computer help find problem.
And finally, something called time frequency analysis. This is for signals where the frequency content changes over time.
Like brainwaves changing as you fall asleep.
Perfect example.
Yeah.
Or analyzing a heart murmur. You need tools that show you both when something happens and what frequencies are involved at that moment. More advanced techniques like wavelets fall here.
Wow. Okay. So quite a sophisticated process.
Absolutely. And connecting these objectives back to the real world, it shows how vital BSP is.
So ECG analysis uses this for?
Detecting arrhythmias, irregular heartbeats, or ischemia, which is reduced blood flow. Potentially life-saving stuff.
EDG analysis.
Diagnosing epilepsy, sleep disorders, monitoring the brain during anesthesia to ensure patient safety. Really complex applications.
And EMG muscle signals.
Assessing muscle function, diagnosing neuromuscular diseases, even controlling prosthetic limbs sometimes.
Prosthetics. Wow.
Yeah, reading the intent from the remaining muscle signals. Then medical imaging, MRI, CT, ultrasound, processing the raw signals to build and enhance those pictures.
Sharper images, better diagnosis.
Exactly. Telemedicine, too.
Yeah.
Processing patient signals remotely in real time.
Crucial for remote care.
And all those wearable health devices, they're constantly processing sensor data using these techniques, plus underpinning so much biomedical research. It's fundamental.
It really does seem like the backbone of modern medical tech in many ways.
In many ways, yes.
But it sounds complex. It can't be easy. There must be challenges.
Oh, absolutely. It's definitely not straightforward. Designing systems to handle this, it raises tough questions.
Like what? What are the main hurdles?
Well, the lecture pointed out a few big ones. First, variability.
Meaning?
Signals are incredibly different from person to person, and even in the same person. They change constantly depending on activity, stress, health.
So no one-size-fits-all algorithm.
Not really. You need adaptable systems.
Mm-hmm.
Second, noise and artifacts. We touched on this.
The signals are dirty.
Very dirty, often. Contaminated by electrical noise, muscle movements, equipment interference. It's like trying to hear a whisper in a hurricane sometimes. Requires very robust cleaning methods.
Makes the filtering step critical.
Hugely critical. And third, real-time processing. In many cases, you need the results now.
Like in an ICU. Or a wearable giving instant feedback.
Exactly. The processing has to be incredibly fast and efficient. Can't have delays when a life might be on the line or when you want immediate insight from your watch.
Speed and accuracy under difficult conditions.
That's the challenge.
So for someone wanting to actually build these systems to get into this field, what does that involve? What deeper mechanics do they need to understand?
Well, you'd really dive into the mathematics and engineering. The lecture's course content gives a clue. You'd study different types of transforms in depth.
Like Fourier, we mentioned.
Fourier, yes, but also Laplace, Z-transforms. Tools to analyze signals in different domains.
Yeah.
Reveal hidden patterns.
Different ways of looking at the data.
Exactly. You'd master digital filter design. Really understanding how to craft filters, IIR, FIR filters, concepts like poles and zeros, to precisely shape the signal, isolate what you need.
More than just basic noise reduction.
Oh, yes, very sophisticated design.
Yeah.
Then signal modeling. Techniques like ARMA models, ways to mathematically represent the signal or the system producing it, helps with prediction or understanding.
Building a model of the signal.
In essence, yes. More advanced time-frequency analysis too, STFT, wavelet transforms for those complex, changing signals.
Going beyond the basics.
Right. And even understanding the hardware, the specialized computer chips, the DSPs, digital signal processors that actually run these algorithms efficiently.
Doing the tools in the engine running them.
And finally, specific application notes. Really practical stuff, like how to properly analyze heart rate variability from an ECG, or process EOG, EEG, EMG in detail for specific clinical questions.
Getting into the nitty-gritty of applying it.
That's right. And to really master this, people rely on foundational textbooks.
Right.
The lecture mentioned classics by Porokes and Manolakis or Oppenheim. These are sort of the Bibles of the field.
The deep knowledge base.
Exactly. That's where the really groundbreaking work builds from.
Wow. What a fascinating journey today. We started with just the idea of a signal, this function carrying information.
Seems simple, but it's profound.
And we saw how they're just everywhere. Music, images, and crucially, the electrical buzz inside our own bodies.
Yeah.
Then we unpacked signal processing, the magic that makes sense of it all.
The toolbox.
And zoomed right into biomedical signal processing, seeing how it translates the body's language for diagnosis, for monitoring, for wearables. It really connects the dots, doesn't it? That aha moment about the invisible world.
It really does. And it makes you think. Consider the incredible potential still waiting to be unlocked. We're listening to these subtle internal signals our bodies make constantly, but as our ability to extract more and more meaningful information evolves, what new frontiers open up in health and diagnosis, maybe even in enhancing well-being?
Deeper understanding, perhaps.
Maybe. How will this ongoing internal dialogue, once we can decipher it even better, change how we understand ourselves and manage our health? It's something to ponder.
That is a powerful thought, a future where our bodies might communicate with us even more clearly. Well, we hope this deep dive has given you, our listener, a new lens to see the world and yourself through the concept of signals.
Keep listening, keep observing.
Thanks for joining us on this deep dive.